Okay, thank you. Yeah, so I'm going to be talking actually not about Scala stuff today. I'm going to be talking about Python and Spark. But it's all running on top of Scala code at the end of the day, so we can just squint and pretend. And yeah, if you want to follow me on Twitter, it's Holden Karau. I do occasionally tweet about computer stuff. Right now, mostly really depressing stuff. So maybe don't follow me for 3.5 years. Oh, clicky device? Oh, damn it. No clicky device for Holden. OK, I will. Yay, OK. So I normally have Boo as my co-presenter. She comes with me to almost all of the conferences, but we gave her a bath this morning, and she wasn't quite finished drying off. So she's at home. Don't worry, though. She's doing fine, and she will be with me the next talk that I give. Right, so yeah, my name is Holden. My preferred pronouns are she or her. I work here. This was the least far I've ever traveled to give a meetup talk, so thank you all for coming to me. I really appreciate that. I'm very lazy. And yeah, I'm a Spark committer, and I've worked at a whole bunch of places, including Foursquare, which has not yet gone bankrupt. I checked this morning, and their application still works. So it's exciting. And I'm a co-author of a few books. I'll try and get you to buy them too later. And this is just not related to software so much, but after the sadness of last year, I added this slide just in case you don't happen to know people like me. I'm trans, I'm queer, I'm Canadian, I'm here on a work visa, one of the ones which people are talking about changing, which is just not at all stressful. And I also consider myself a part of the leather community. And I write the same really bad Spark jobs that everyone writes. I get out-of-memory exceptions from my code too. There's no secret, like, queer Java garbage collector that we've been hiding from you. We're nice people. If we had a better garbage collector, we would share it with you. So, you know, be kind to your colleagues, especially the ones that need hugs. Yeah. Rockin'. Vijay already did this slide. Is he still here? He is. Damn it, I can't make these jokes. But you may have noticed our very green lobby as you were walking in. And I like to think that this is why we make really good software. It's not the people that work here. It's that we have this green lobby. And this should convince you that we make only the finest Python and Scala code. So I'm hoping you're all nice people. I'm really curious. How many people know about Apache Spark? Like, OK, awesome. Now, how many people have no idea? Like, this is their first time they've heard someone talk about Spark. It's OK, don't be shy. OK, there's like one person, two, OK, and a few more hiding behind the cameraman. OK, lovely. So I'm going to be talking about the magic behind PySpark. And it turns out the magic behind PySpark is 300 small gnomes hiding in a box. And if this is your introduction to Spark, this might be kind of a scary talk. Please don't be scared away. All distributed systems are terrible. We're just talking about how Spark is terrible, but don't worry, everything else is bad too. Hopefully you're interested in making Spark jobs work better, and by finding out how Spark is terrible, we can avoid the parts that are going to like steal our cookies and our lunch money. So for the people that are new to Spark, it's general purpose distributed computing. It's awesome, it's magical, it totally fixes all of your problems. Buy a support contract from IBM today. I'm told we even have products, IOP, right? That's an IBM product? No, you're shaking your head. OK, whatever. If an IBM salesperson comes to your office, you want to buy whatever it is they are selling. I kind of failed the marketing training class that they made us take a few times. But yeah, so Spark is an Apache project. It's not an IBM thing, but we contribute to it. We've got a lot of other people here working on it. And there's some people down the road at Databricks working on it, and there's some people up the road at Cloudera working on it, and there's some people who like work all the way down in the South Bay, very, very exotic location, and Hortonworks working on it, and people in other countries too. So most people come to Spark because they're like, MapReduce, that is so last season. I need something new to convince my CTO to give me a bunch of money. I'm going to use Spark. The other reason people come to Spark is they're like, I'm getting a lot of out-of-memory exceptions. How hard could it be to do distributed computing? And then it turns out, yeah, kind of. But yeah, let's just go on to the next slide. Yeah, right. So this is the cat who's come to Spark because they're like, well, my MapReduce job is going to take 16 hours. If I drink a lot of coffee, I can probably learn Spark in those 16 hours. And you can with one of my handy new books. And the other one, yeah, and this is the other cat. This cat has found out that pandas runs out of memory when you run it on a MacBook Pro. And they're like, I know, I'm going to use distributed computing to solve my problem. And the other reason that people use it is there's a magical cat and 600 gnomes inside of it. Not a guarantee. OK. So what is the magic of Spark, right? Like, we all know Spark is amazing and it's in all of these fancy magazines. But like, presumably, it does something different than MapReduce and all of these other distributed systems. But so what is the magic? I think the key magic is this thing called the directed acyclic graph, which, if you spend a lot of time in grad school, sounds like a very reasonable thing to name something. And if you finished undergrad, like me, it sounds like someone spent a lot of time in grad school. But we can just think of it as like a query plan, but like less fancy. We can think of it as being, that's where the 300 gnomes are hiding out. They're going to hide out inside of our directed acyclic graph. And then our optimizer is going to be able to look at our really fancy query plan and do some really cool things. The other part, which is really important, is Spark has a different resiliency model than other distributed systems. Traditionally, distributed systems often depend on doing things like on multiple machines and then writing the results out to a bunch of different machines so that when shit goes wrong, so that when things, god damn it, so that when things go wrong, it can recover by just going in and reading in the missing data. But in Spark, its approach is like, nah, whatever, that's cool. If something goes wrong, I like have this query plan. I'm just going to go back to my query plan, figure out what it is I was trying to do, and I'll just recompute that missing data. And it turns out recomputing some missing data is often a lot faster than writing to 3 disks over a network. Writing those 3 disks over a network is kind of slow. The other thing is, like, we got some cool magic stuff, but let's just move on. We can just skip this one. We got mostly Spark people. Right, so this is our magic, yay! And the other really important thing that I think we don't talk about a lot is that RDDs don't really exist. At the end of the day, an RDD is actually really just a query plan. And it's kind of like a 16-year-old. You ask it to take out the garbage, and it says, yeah, I took out the garbage. But it's only once you actually go and look to see if the garbage got taken out that it gets around to actually taking out the garbage, right? And if you ask it to do a bunch of different things, it'll put off doing all of that work until the very last minute. And unlike a 16-year-old, it'll actually probably do the work better as a result. Because it knows, like, oh, I have these 5 different things I need to do, I can combine a bunch of these steps together for you. And this is really cool. I think it's awesome. And so here's a picture of what the DAG looks like. We can see, like, we've got essentially some data coming in. Here I was reading in text files because I'm lazy and Parquet is too much effort. And then I was doing a bunch of sort of functional programming stuff on top of it. And so that's pretty cool, right? But Spark has figured out that it can combine a whole lot of these steps together. And it can actually even figure out that it didn't even have to do this step because it had this data cached for me. But here it was like, oh yeah, you asked me to like do a bunch of things on the same piece of data, but I can just push all of these things together into one operation inside of Spark. And this is really important because iterating over our data is kind of expensive, right? Like, if everything fits in memory, that's great. But if I have to like pull stuff in from disk and like do that stuff, doing multiple passes over my data gets really expensive. So being able to combine it is awesome. The other thing is there's this thing called query plans for DataFrames. How many people are using DataFrames? That's not everyone. I'm so upset. Just fake upset, fake upset. Query plans are awesome. DataFrames are really cool. They allow Spark to sort of see a whole bunch of things that are going on. So here, Spark really just sees like, I was doing some cool functional programming business and like, ooh, fancy. But here, Spark sees like, hey, you were doing some aggregations. I can optimize aggregations and do really fancy things. And so there's some extra pieces of information inside of the query plan. Right, and our traditional word count example. You should all be familiar with this. As you've noticed, it is in every big data talk ever, except for Fred's talk, which was right before mine. And he will probably be hearing from the licensing bureau, like I did the last time I left it out. That's why this has to be in all of our talks. If we leave out word count, they take away our license. And as a foreigner, I really don't want that happening. Now is not the time to lose my big data license. So I've got word count in Python, and so I've got some input data, I do some work, and then I save my results out. And then we go to the next slide. And this is the slide where our 16-year-old has to take out the garbage. So once we do this action, right, we sort of force Spark to do its work, but it can combine a lot of these previous steps together and do less passes over the data, and it can do some fun stuff as a result. Now this is really awesome, and we've talked about how it's cool, and it can do this pipelining. That's really fun, but people don't seem super excited, so we'll move along. And it turns out that this pipelining stuff, it's really cool, but the magic only goes so far, right? It's like we went to Hogwarts, but then we didn't really pay tuition, and we got kind of kicked out. That one needs a bit of work. Okay, so it doesn't have a whole program view, and this is the biggest problem with Spark. From the point of view of like an optimizer, right? Spark can see what we're asking it to do, right? Like when it got to that part where we asked it to take out the garbage, like Spark was like, oh, I know all of the things I need to do to complete this step, but it has no idea what is coming next, right? If we do a second thing, if I take those word counts and I put them into my awesome, totally real business logic, then Spark is going to recompute all of those word counts for me, and that's going to be kind of sad. And so this sort of limits what can go on. The other part is it can't see inside of our map functions, right? So when I take data and I tokenize it, like we did on the previous slide, Spark doesn't really know that I'm tokenizing the data. It knows I have this function that it's running, but it doesn't really have any idea of what's happening inside of my functions. But there's some more magic, and we'll talk about sad things later. But our data is magically distributed. Yay! Come on, oh, God damn it, this crowd is hard. Fine. So okay, the other really important thing is that our data is magically distributed. So our RDD splits the data up onto all of these different workers for us, and at the same time, it splits up the work that has to happen on the data to the workers that have the data. It's very convenient that way. It does shuffles for us, so if we have to join data together, it like figures out where everything goes, and it does really awesome stuff. And we'll skip the bottom part because, yeah. Right, so when we say distributed, what we mean is 300 gnomes. And each one of these gnomes has a little piece of our dictionary or whatever it is that we're building, and then we go to each gnome and we ask it to compute whatever piece of data we need. The only problem is when we do something where we have to like sum up our results from each other, all of the gnomes have to talk to each other, and that goes kind of bad. Now, thankfully, computers don't drink as much as gnomes, but like this can be a really bad and hard thing. And this is where keyskew comes to the anti-rescue. I need a better word for that. But maybe villain? I don't know. Keyskew could be a villain. Zip codes. No, okay. I'll figure out a good magical cape for that. But so keys aren't evenly distributed. And this is a really big problem with real data. With fake data, it's great. I can use the random RDD generator, and I can make some really nicely evenly distributed stuff and pretend that I don't have keyskew. But if I work with humans, they have this inconvenient property of clustering together in cities. And it's just, if they were just normally distributed across America, it would be so much easier to do all of these statistics. And there's all of these other clustering, like by age. It turns out humans aren't evenly distributed across the range of 2 to the 32. Like, who knew? So when I group my things together, things go kind of poorly. And so what happens is, instead of splitting up our work evenly amongst those 300 gnomes, one of those gnomes becomes responsible for New York City, and that gnome gets really depressed. That gnome just doesn't do a good job, and if you're lucky, you maybe get an answer from that gnome, like at the end of the week. But if you're unlucky, that gnome just gives up and drinks, and then your job fails and you don't know what happened. Drinking gnomes. Yeah, and so here we can watch one of the cases where gnomes are going to fail. Oh, I love this example. Okay. There are no, yes, okay, sorry. So this example, in which zip code do you live in?
94107.
Oh, damn it. Okay, close enough. I'm going to pretend you live in 94110, but whatever. So this is my example for what I want to do after I get out of the software industry, because this is kind of bullshit. Fuck, God damn it. Okay, yeah. So I've got a bunch of information about where people with handlebar mustaches live. And I've decided to open an artisanal mustache wax shop. And I'm really excited about this, but I need to figure out where to put my artisanal mustache wax shop. If I put it in the wrong neighborhood in San Francisco, I'll go bankrupt and I'll have to get a job in software again, and that's gonna be sad. Yeah. And so here, if I took my data and I tried to sort it to figure out where I should put my artisanal mustache wax shop, we can see one of my gnomes has far too much data, and it's the gnome who ended up responsible for the Mission District, because there's a lot of handlebar mustaches out there. And that gnome just gives up and goes and days drinks in the park, just like the Mission District. But so we can see that this goes poorly and we don't get an answer because there's too much data. But it's okay. We can just help Spark out, and when we have key skew, we can allow Spark to do splits within the same key. And we do this by kind of doing bad things to our key. And we add some letters to it. And you might be going, Holden, why doesn't Spark do it, Spark self? It's supposed to be magical and fix all my problems. I read that in InfoWeek. I don't actually know if they ever said that. But it turns out that the problem is we have deterministic partitioners. So because Spark, when we do the shuffle, all of the data with the same key has to go to the same gnome or node. Gnome node. And so then it's sad. But now we can make it so that we've got different keys and everything will work out just fine. And clearly, right, we don't have to have all of our data on the same machine when we're reading it in. This rule only applies when we're shuffling our data. And so after we've done a shuffle, we can go ahead and turn these back into regular keys, and everything will be fine, and we can do our processing. It turns out that we can combine this sadness with another kind of sadness to get extra sadness. I actually really like gnomes, but in this example, they're just not going to have a good time. So there's an even worse way to do word count. Let's look at that. Yeah. Okay, so we can tell the cat is getting covered in water. So this is going to go poorly for at least the cat and probably whoever was silly enough to take that picture. So we read in our data, we tokenize it. Things look fine so far. We group it together by key, and then we sum the values. And then we save it out to a file called boop, because I like boop. Okay, and so I did this on kilobytes of data so that the job would succeed and we could actually see what's happening. But we can see here, we have an input of 385 kilobytes, genuine big data. Please buy an IBM support contract. We have a shuffled write of 424 kilobytes. Once again, genuine big data, and a shuffled read of 48 kilobytes. Go to the next slide. Oh, damn it, there was supposed to be a slide where those numbers were lower. Moving on, but if we think back to the previous slide, we note that this number here was bigger than this number here, and that's sad. When your data gets bigger, that's not normally happy. There's this saying, the cross product of big data and big data is an out of memory exception. And so what do we do instead? Instead of group by key, we can use reduce by key. And this is because when we tell Spark to group things together by key, it's forced to make a list of all of the things for that same key. And if we do reduce by key, Spark can actually see what's happening. If we go back a slide, oh, 2 slides, sorry. Right, so this black box thing that I'm talking about is that Spark can't see inside of this lambda expression. It has no idea that what we're doing is just this really simple sum. If it could see inside of this lambda expression, it could move that up for us and do really happy things. But because it can't introspect Python or Java code, it can only sort of see this part, right? It can see map values and group by key. The optimizer is sort of limited. Now we go forward 2 slides, yeah. 3 slides. Oh, this is the one where the numbers are lower. Yay. And so we can see here that we have a number, then we have a lower number, and then we have a much lower number. And so this is when we use reduce by key. What happens is Spark reads in the data, it applies the reduction on each of the individual machines, and then it shuffles the reduced version. And so each gnome only has to deal with the information about how many handlebar mustaches are in each zip code, rather than having to deal with a list of everyone's handlebar mustaches per zip code. The alternative is we can use DataFrames. Yay! Yay! Yeah, okay. DataFrames, raise the roof. Oh, damn it, there's a video camera. Well, whatever, I've done stupider things on video. So DataFrames are really awesome. We can escape back to RDDs if we get in trouble. But the cool thing is DataFrames gives Spark Optimizer a chance to understand more about what we're asking it to do. It does limit what we can express to some degree, but there's so much cool shit that it's worth it. Let's keep going. Let's look at some cool shit. So we can do a functional and relational word count together in Python. And so here we load our data. Once again, I tokenize it with the very high quality space tokenizer. I construct these row objects, and then I group it together by key, and then I take the sum. And this group by is actually safe. It's a safe group by. It's friendly. It doesn't stab us and take our lunch money. I like this one.
Wait, it's safe because it's in Python?
Yeah, let's go back. So why is this safe? So this is safe because it's on a data frame. And so what's happening here is instead of giving it a lambda expression afterwards, we're calling it with like this named sum. And there's a whole bunch of different kinds of aggregations that we can do. But essentially, because it knows that we're doing an aggregation and we express which aggregation we're doing, it can pipeline that aggregation intelligently for us. We don't have to manually do it with writing reduce by key. And not to knock reduce by key, like it's pretty okay, but like, if I want to keep track of like 6 different aggregates, I have to like keep track of like x1 through x probably 12 because I'm really bad at naming variables. And like I'm gonna get them wrong, and then I'll report the wrong average sales to whoever it is that cares. And then I have to find a new job again. And like I only want to do that every 18 months, not every 6. Joking. I love my employer. They are perfect in every way. Right, so we can see here group by key on RDDs is pretty bad. If we do reduce by key, it performs pretty okay. And this is in Scala. But if we do it in DataFrames, it performs even better. And that's because the DataFrame Optimizer gets a lot more information. It knows what we're asking it to do. And it gets to put extra sprinkles of magic on our code. And it gets to use really efficient representations of everything. Yeah, our final bit of magic is how Python and Scala work together to be friends, or at least frenemies. And this part is sad. This is the part that might scare you away. I'm sorry. But it's okay. PySpark is essentially an answer to the question of how expensive is inter-process communication. And the answer is kind of expensive. But with an IBM support contract, you just buy twice as many nodes and pay twice as much for support, and your problems are definitely solved. Yeah, that was it. So this is our detour into the internals of PySpark. This is what a playground would look like in my home country and not in yours. I don't think. My understanding is that you have lawyers. Let's go on. We have lawyers in Canada too. They're just busy suing over Tim Hortons. So Spark is in Scala. How do we make this work, right? Besides just showing pictures of playgrounds, I need to make the IPC work. So Spark has this concept of a program called the driver program. And we can think of our driver program as sort of the coordinator. It's the one that tells all of the other gnomes what it is they need to do. It asks all of these gnomes to do work for it. And on the driver program, we use this thing called Py4j. And Py4j is this really interesting library for calling Java from Python. And it kind of works. Pretty much almost some of the time. But that part is okay, because the driver program is, while it's the part that you work with the most, it's also kind of the least important part, because there's one of it, right? If something is slow on the driver program, it's only slow for one gnome. But when the things are slow on the executors, all 300 gnomes do something slowly, and that's where things get sad. Like, if one gnome wants to drink, that's not my problem, but if all 300 gnomes are drunk, I have a problem. That used to be funny. Okay, next slide, quickly. So what does this architecture diagram look like? So besides illustrating the fact that Fred has access to the designers and I have yet to trick them into working on my slides, this architecture diagram indicates that each worker has a Java process that communicates over Unix pipes to Python. And I think the really awesome thing about this architecture is that it somehow works. I'm like super impressed. So what happens is the Java process will go out and read some data from HDFS or S3. What's the IBM version called? Or IBM whatever it is, Object Store? Okay, Object Store. And then load it into memory, and then it'll get copied over to Python, and Python will do its fun, like it'll do NumPy and Skippy, or Pandas, and all those happy things, and then it sends the result by Java. And then they talk to each other, and then the data gets copied back and forth a lot. So how does this break, right? Like, this wouldn't be a talk from me if it wasn't about how life is terrible. And so it turns out the main thing that sucks is that we have to serialize our data a whole lot. Every time we copy our data from Python to Java and back and forth, we have to serialize it. And we serialize it using a thing called Cloud Pickle, which sounds nice. Clouds are fluffy. Clouds are good. You can buy them from companies, right? And they're the future. But it turns out Cloud Pickle is really just pickle. And someone called it Cloud Pickle because that sounded a lot nicer than pickling my data. We Cloud Pickle it. Yeah. The other parts are all, like, these are all things that are bad. They're far less important than this one, though. Yeah, that's fine. We'll just look at that one piece of sadness. So what do our gnomes look like? So I've said that we actually have 300 gnomes, and this is how caching is implemented in PySpark. It is, well, I can read this because I spend far too much time reading this code. But it turns out that like almost everything in PySpark is just really simply asking Java to do all of the work for it. And that's really cool because it lets us just take all of the work that Java people did and just like copy it, but without even having to rewrite it into Python code. Because like, I don't know how to rewrite a factory into Python. That's just going to make me sad. I can just call the factory and everything will be fine. Right, and this is even super more important. I should have put this slide elsewhere, but if we think back a while when I was talking about why you should use DataFrames, this is super true for Python users. So this like double serialization cost means that reduced by key, like it works, right? Like it succeeds. It's still twice as fast as doing group by key, but like doing it in DataFrames is so much more awesome because when we do it in DataFrames, PySpark is able to take what we're asking it to do and compile it down to JVM JIT code for us. And that's just amazing. I can like write my Python code and have that stuff run inside of the JVM for me. And I can even pretend it doesn't exist until I get an exception. And then I give up and I drink like a gnome, but that's future Holden. And there's a bunch of future things happening. I think they're really cool. There's this thing called Apache Arrow. I think it's really awesome. It gives us the possibility to do interchange between the JVM and Python without using Cloud Pickle all the time. And if we can manage to convince the Spark community into using Apache Arrow, I'm going to have a little party, and you're all welcome to come to my party. It's BYOB and downstairs in front of the place until the security guard kicks us out. But it's pretty fun, and it'll give us like a really good 2x speed up. The other thing is, if you work with PySpark, I really want you to share your UDFs with me. Please share the things that you're doing inside of your Lambda expressions with me. I keep trying to trick other people into doing things that will make Spark faster, but they keep coming back to me and saying, like, I don't believe your benchmarks, and that's just word count. And like, I can make more fake benchmarks, but if you can like give me things from companies which aren't mine, I can try and convince people that the changes I'm proposing are useful for like at least 3 people. Because right now I've got them convinced I think it's a funny idea. And the last time they merged that code, it went really bad. So like I need a new strategy. Right. There's a bunch of really cool things. You should buy Paco's Introduction to Spark video if you have an expense account. But I have a new thing that I'm trying to sell you, so we're going to skip this one. There's a bunch of Spark books. Don't buy this one. I'm really sorry. It's out of date. I really wish we'd stop selling it. I mean, if you want to give me money, IBM compliance training said I can't take $20 bills in brown paper envelopes. So you could just buy a lot of copies of this book and like send me a nudge, nudge, wink, wink. Oh god damn it, the Germans are in the back. There's Learning PySpark, which is from some of my friends. I owe one of the co-authors of this book a beer. And if you buy it, please let him know that I don't owe him a beer anymore. His name is Denny, he's lovely. I'm sure it's a very good book. But the best book is the one that I make money on, so let's skip to that book. And yay, you can buy it today. Normally I have to try and sell people a book that doesn't exist, but it exists. So you can buy it from OReilly today, and I get the best royalties when you buy it from OReilly directly. So if you have a corporate expense account, this is the gift of the season. If you have cats or dogs, just please buy several copies. I like drinking coffee, and drinking coffee in San Francisco is expensive. If you want to buy it from Amazon because you hate me and you don't want me to get as much money from royalties, it'll be available from them in a few weeks. But you can buy it from OReilly today. Oh yeah, if you want an excuse to come to Berlin, Porto, Vancouver, or somewhere in Australia, I should really figure out where. Someone told me that's kind of a big country. You should come join me at one of these conferences. I'm sure they will all be excellent. Does anyone want to go to Berlin?
Yes.
Come join me in Berlin. Tell your boss it's super important. I don't remember what I'm talking about, but I'm sure it's good. Okay, so that's pretty much it for me. This is another one of my stuffed animals. So yeah, okay, bye. Does anyone have questions? Or do I just like run away to the side? Damn it. Oh wait, yay. Thank you for asking that question. So the question was, do DataFrames offer any improvement in portability between the JVM and Python? And the answer is yes. So underneath the hood, RDDs in Python are RDDs of pickled strings, and that's just depressing. If you want to try really, really hard, it turns out you can parse pickled data in Java. Just no one wants to, and you shouldn't. But DataFrames actually represent all of their stuff inside of the JVM heap in a format that Java can understand. And we know how to transfer it to Python. So if you use DataFrames, you can actually call into Scala libraries that take DataFrames and use them from Python. You don't have to wait for Python libraries. Admittedly, doing that is one of the ways that I have accidentally summoned Cthulhu, but I convinced them that my soul had already, IBM owned it at this point, so it was time to go back to the underworld. But you know, it's doable. It is a little, what's that expression? You can do it. If it breaks, I'll blame you, unless you bought a really good support contract. That's like the support contract where you can like make an engineer show up. I don't know how much those cost, but like, yeah. But please do that and make your startup's code depend. No, not startup. Make your company. You're like publicly traded. Make your company's code depend on this really complicated feature, and then like I can make money. Wait, no, that's not why I do this. Software, yay! Okay. I'm sorry, y'all. Were there any other questions or? Oh, yay! There's a second question.
So one question is like, is it really like the lambda function or the map that maps the lambda function on our data frame or RGB that is small? And another question is, you mentioned about EAPs.
Yeah.
So if we have like cross raw, basically.
Here, let's do it one at a time. I'll answer your first question, and then I'll answer your second one. Otherwise, I'll forget your question part of the way through. I've done this. So the first question is it my lambda expression that's slow, or is it the mapping part that's slow? And the answer is like, yeah, your lambda expression in Python is a little slower than the same logic expressed in the JVM. But the expensive part is really just copying the data from the JVM to the Python executor to interpret. It's not that your lambda is slower, it's really just the copy. And I actually have this really interesting proof of concept using Jython, where you avoid the data copy and you still do Python evaluation on the data. And it runs within 5% of Scala native code performance. The only downside is it adds 100 meg jar to the Spark dependency, and when I tried to get them to take that pull request, they just laughed at me. So that's not happening, but Arrow is going to fix the copying part, and things will probably get a lot better in like Spark 2.4. And the second part of your question, I cut you off. Do you still have it? Okay, maybe later. Yay! All done. Next speaker! Yay!